This is the first of our current electricity videos. We're talking about resistance and resistivity. So what is resistance? Resistance is the ability of an object to resist the flow of electric current. Okay, so thank you for defining something with something I don't know. So what is electric current? Electric current is the flow of positive charges. Thank you very much, Ben Franklin. Okay, Ben Franklin had a 50-50 choice. When he defined electricity, he chose wrong. But basically, we know now that it's not the positive charges that move, because the positive charges are basically our nuclei. Okay, so we have positive nuclei in the atom. And it's our electrons that move. Okay, so when the electrons move from here, whoops, I can't move just an electron. When just one of our electrons moves, it moves from here and it moves down the chain. And when it does that, it leaves behind a positive area. So as the electrons move down this way, we see that our net positive charge here is going to move in the opposite direction. So that's going to be our current. And the abbreviation, the variable that we use for current is I. And current is measured in amperes. And an ampere is basically a coulomb of charge. So it's our charge per second. So amps, so an amp, that's generally how we talk about it. An amp is our charge divided by our time. So what's really funny is we talk about resistance when we're talking about conductors, which is kind of an oxymoron a little bit, because conductors allow current to flow through them, but conductors also have resistance, and here's the reason why they have resistance. So as we have a wire, and we've got this a little electron here, and he's trying to go through the wire, he's like, oh, I gotta talk to you, oh, gotta talk to you, gotta talk to you, gotta talk to you, talk to you, talk to you, and he's bouncing his way through. So do you see how he got slowed down? Resistance slowed down on his way through the material. And the thinner our wire is, so if we make our wire really, really thin and we only have a few atoms, then when our electron goes through here, it has to interact with each one of these guys on its way through. So a skinny wire is going to slow it down even more, whereas this bigger wire, when we do the bigger wire, our electron can go, oh look, I can go this way, I can go that way, there's got multiple paths that it can go, so it doesn't have to wait for the electron in front of it to make its way through the path. On the small one, okay, only one electron can get through at a time, whereas on the fatter one, you know, this electron can go here. If we add another electron, it could go down here. And so more electrons, because there are more pathways, can actually get through the fatter wires. So the area is a factor in the resistance. If we have a larger cross-section area, like we do in this one here, if we have a larger cross-section area, we have a lower resistance because there are those more pathways. If we have a really small area, there's only one pathway, so the electron has to wait for the one in front of it to go on, and so that one is going to have a larger resistance. So area, how fat the wire is one of our factors that's going to determine how much resistance it has. The length of our wire is also a factor. The longer our wire, Okay, remember it's talking to the atoms on the way through, so the electron's having troubles getting through. So the longer that wire, the more resistance it has. And a short wire, it's like, I gotta talk to you, talk to you, talk to you. Oh, good, I'm through. Whereas this guy, talk to you, talk to you. This is like a long tunnel. This is like driving through a super long tunnel where you can't really pass anybody, and then finally I'm out, so you can go through. Slower through this one, you go really fast, and really fast once you get out. So the length. So if you have a longer wire, you have more resistance. A shorter wire, less resistance. The last factor that determines what resistance a wire has is the resistivity of the material. Like density and like specific heat capacity, these are actually properties of the wire itself. Remember that as the electron goes through here, it's interacting with all the nuclei. Well, some of those nuclei are going to hold on to the electron a little bit more than others. So they're going to be like, wait, you can't leave. And so it'll say, okay, I'll stay, but I really got to go. And it'll go. And then, oh, and the next one, I want to talk to you. I want to talk to you. And so the electron has a harder time getting through if you have a higher resistivity. And it has to do with what metal it's made of. Some nuclei, which is, oh, yeah, go. Okay, no problem. They have low resistivities. Other nuclei are a little needy, and they want the electron to hang around for a little while before it can make its way through, so it's going to have a higher resistivity. So remember, the resistivity, that's going to be a constant that you're going to be given, and it is dependent on the actual material itself. And I'm going to show you a table of resistivities. Okay, so here's a table of resistivities, and you notice our insulators here. Our insulators have really high resistivities, meaning they're not letting their electrons go. But our conductors are going to have really low resistivities. And so these guys let electrons go through a little bit easier. And then you see how it depends on, am I made out of lead, iron, tungsten, aluminum? You know, silver has a really super low resistivity, but, you know, is it very cost effective to make our wires out of silver? No. That's why we use copper more than we use anything else. See how copper has fairly low resistivity? That means it's going to let electrons go through fairly easily, and that's why we make most of our wires out of copper. And so all together, here's how we calculate our resistivity, or our resistance. So our resistance, whoops, sorry about that. Our resistance is equal to our resistivity. You see in our table, resistivity is given with the Greek letter rho, which I wrote wrong, so let's fix that. Rho times the length, because remember, your resistance, as you have a longer wire, you have greater resistance, divided by the area, because remember, as you have the larger area, you have more pathways, and so your resistance is lower. So this is our resistance equation, and we measure resistance in ohms. So ohms, that's how you spell it. It's kind of fun to say. It's the Greek letter omega, so you're going to see like 10 ohms for your resistivity, or resistance. This is resistivity. This is resistance. Resistivity, constant. Resistance, a combination of all of this stuff. Now, the resistance of a resistor is a property of how it's designed. So once you've made your resistor, it has that resistance all the time, and we will reiterate that in a lower video. All right, good to go. See you later.